Hi, everyone. Hope you're doing well. So it looks like we have maybe half of a TA. They're still trying to figure out who's going to be the TA for the whole class, but maybe we have one for Friday. Otherwise, I would do it again. So that's life. I think I didn't do too bad. You be the judge. Anyways, so let's continue on our journey. So we have all the material we need to do the first homework assignment. I haven't posted the material for the TA session of Friday. Depends on where what we reach today, and accordingly, I'm going to decide which exercise I give you and which one you need to finish for Friday. All right. I don't think it's very useful to go over the quiz. I've looked at it and it looks pretty easy. I don't remember if I created one for this week. Otherwise, I'm just going to give you some exercise. Yeah. So don't worry about it. Okay, so let's, without further ado, let's start. Okay, so solving quadratic equations. Somebody remembers the formula for a quadratic equation? So if I have something like ax squared plus bx plus c equals 0, find x. Is that ringing a bell? I hope for at least one of you. Yes, minus p plus or minus for oh, you can't hear my voice. Sorry about that. I just checked and it was supposed to be working. Okay, so yeah, I checked it and it looked like it. So probably it's on your side. All right, so let's. I'm not just going to reiterate it. So let's just go a bit further. And where did that come from? So this has been known for quite a long time, this formula. Higher orders are much more difficult, but some formulas exist. Yeah, or rather, I didn't. Where did a formula come from? So the trick here is that we want to get rid of x squared, right? So the idea, get rid of x squared. So if we could have an expression which would be a perfect squared, where x is inside it, we'd be good to go. So that's the whole idea, is we're going to create some sort of expression in which x is inside it, and then we can just say it's equal to something else and then take the square root on both sides. So yeah, where does so perfect squared? So it looks like this, of course. So if you have like v plus w squared, so it's equal to v squared plus 2vw plus w squared. So that's what we're going to reproduce here on the left-hand side. And then we're going to have some other stuff over there, but we're going to be done. So let's just go and do that. So first of all, let's make our lives a bit easier and divide by a on both sides. So this is valid. It's just I divide by a on both sides. I still get that. But I could not do it, but I think it makes things a bit easier. All right. So what is v? well, v squared is x squared. So here, what do I need? I need 2v and multiplied by something else. So here, let's just make appear 2v in front of that. So how are we going to do that? Well, let's multiply by 2 and divide by 2, or rather, let's put 2. Then we have x here. So as you can see, we are almost done. So we have x squared plus 2x, which is this, times, so this would be our w here simply. All right. So then last thing we need to do is say, all right, so then to have a perfect square, I'm going to have to need, so yeah, let's put just the 2 at the bottom there. So this is our w, so plus w squared. And then, of course, I'm adding w squared. I'm going to add w squared on this side as well. And what I can do is just subtract c over a on both sides and get this, all right? So this is a perfect square. It's x plus b over 2a squared. Makes sense? So if it's going too fast, you can just try that on your own. So yeah, so then this is, yeah, I can just write it here, x plus this squared. Is 2a the following class? Two away, do you mean the class that just follows this one? Or let me just check. Oh no, I thought it was 326. All right, so the program for this class is lots of linear algebra and then a bunch of calculus stuff, but we just stop short of multivariable calculus. We do some of it. Well, we'll see how fast we go next time. Last time I did some of it. Maybe I won't do as much this time. All right, but yeah, I don't know that class. Okay, so what do we do now? Well, we have a perfect square with x inside it, and we have a bunch of other stuff on the other side. So let's take a square root on both sides. So yeah. So this is going to be equal to plus or minus square root. And then let's subtract b over 2a on both sides. So I get this that goes over here. And then it's just a matter of simplification. Yeah, so that's 4a squared. That's b squared. Then let's have a and a squared and 4 and 4. So I can have this right here. So then, of course, I can just take out the 4a squared and get 2a there. So I can just have this there. All right. So this is where your friend formula came in. Of course, you can just do this for every type of calculation you want to, but yeah, this is much faster. Makes sense? So this is where it comes from. And so how many solutions can I get? So So how many solutions? Yeah, it depends. Oops. If b squared minus 4ac is greater than 0, how many do I get? Two, yes, two. I'm going to see real roots. Because we could have complex. If I allow for complex numbers, we have always have. Well, it's different. So let's not go there. If this equals 0, how many do I have? Yes, exactly. So one real root, which is just minus b over 2a. Or you could also say it's 2 repeated roots. But yeah, it's just a matter of how you call things. And if b squared minus 4ac is smaller than 0, so no real roots, but of course, imaginary roots. So there's no problem if we allow for imaginary thing, but don't worry, I'm not going to go there. So questions, is there similar formula for cubic formula? Cubic equations. Yeah, that's good. So if a is 0, what does that mean? Well, it means I have a simple have x equals if a equals 0, then I'm left with this, right? Oops. So I have x equals minus c over b. Yeah, so that's easy. Yeah, it's linear, exactly. So yeah, and where would that? So why don't I get like nothing? Well, it's because I have so I have some a here and I have some a here. So yeah, it looks like I have. So yeah, if a equals 0, then what would I get here? I would get, if I mistakenly compute it, then this is 0. And this is 0. So I have 0 here, but here it's square root of b squared. So this is b. Yeah, so but I don't get b minus b. So I get something like b plus b. So I get, yeah, plus b or something. So I get 0 over 0 basically. So yeah, I cannot use this formula to solve it. Yeah. Okay. Yeah, no, so just try stuff, just say stuff. We're there to learn. Don't worry about getting everything right. So question there, is there a similar formula for cubic equations? Yeah, you could reduce a cubic to quadratic, but yeah, there is. So yes. So this was like high-tech research back in the Middle Age in Italy. So the Italians were just trying their best to find a solution for a cubic formula, and it took a while, but yeah, it was found by Fubini. Maybe it's a combination of different people, or but maybe that's a mathematician too. I don't know. So I think it's Ludovico Ferrari. No. I think no. It's that guy is for quartic. So yeah, Giro Namo Cardan found it. Yeah, but so there were many. So maybe Fubini was into it. Yeah, found by Cardan. And the way you have to approach it is, yes, to just consider a cube and look at everything that's going on, like you would for a square. You look for a cube, and you can deduce a sort of this sort of equation, but it's of course much more complicated. I'm not going to give it to you. We don't have. And yeah, so Ludovico Ferrari found it for quartic equation in 1545. So that was high tech. He hid his formula, and nobody was going to share it with nobody else, and that makes it more complicated for yeah, attributing it to people if they don't publish anything. But yeah. So somebody knows for quintic. So degree 5. Yes, so it's the Ruffini. Yeah, Abel-Ruffini theorem. There's no general formula for quintic. So it's an extension of the yeah, work by many. So yeah, who's that French mathematician? Have it hit on the tip of my tongue, but I can't remember. Yes, you can find some factors, but it's just yeah, I remember. So Evariste. Yeah, that guy was a genius, really a total amazing mathematician, but he died very young. So yeah, very sad. He would have been like top 10 mathematicians if he had lived longer, for sure. All right, so okay, so let's go back to economics a bit. So the kind of thing that we can have is something like a quadratic demand. Yeah. So this may be useful in some models where you need some sort of nonlinearity that you introduce, and you may have something like a quadratic demand, for instance. So let's have something not too complicated. So QD equals 10 minus p squared. And let's have QS equals 3p. So why don't I let you? Yeah, France Revolution. So why don't you try and solve it on your own? See what you get. So what is Q? Yeah, and let me add a constraint. P and Q are greater or equal to 0. Yeah, I think that's it. Oh, it's funny. It looks like I have many solutions. Okay, let's try it. So thank you, Mr. Wang. Let's see if you got it right. So what I can do is using market equilibrium condition QD equals QS. So I have that 10 minus P squared equals to 3P. So let's put that into a form that is more helpful to us. So that would be minus 10 plus P squared minus 3P equals 0. So P would be equal to so that's plus 49. So that's plus or minus 7. So then I get that this is either equal to 5 or minus 2. So constraint here, P is greater or equal to 0. So we only keep the positive root, right? Oh, did I make a mistake or? Set plus 3, it's 10 divided by 5, right? I think I'm. So one way to just see if we're good is let's check it. So 5 squared plus minus 3 times 5. This is equal to 0. Yeah, so we're good. And that's right? 10 minus 10 minus 3. Oh, yeah, that's the error, the mistake I made. So this is plus. Yeah, okay, right. It's plus, yeah. Let's be more systematic there. Plus P squared and minus 10. Yeah, always trust your student, never trust yourself. Okay, so that would hopefully be better. So what's changing? Or did I make a mistake? No, yeah, I have to keep that one. Yes, so it's -3. So I have yeah, this is still yeah, so it's 2 or -5. Okay, yeah. So we keep the positive root, which is okay. And finding Q. So let's just use this. So QS goes to 3 times 2 is to 6. So then the solution is so let's just say it's Q star P star equals to 6 and 2. Is that right, or is there a consensus now? Should we vote on what is the right solution? Yeah, I'm pretty sure I'm okay right now. Well, okay. One thing we're going to do now is graph it anyway. So if the graph looks very silly, then we know we have made the mistake somewhere. Five minus 2 plus 3. So that's 40, right? Okay. Anyways, not. I'll see if I made a mistake. So let's draw a graph. So for that, we're going to use, so we want to represent the supply and of the supply demand with P on the vertical axis and Q axis as usual. So let's go ahead and draw the, so that's what we want. So for the, let's pick 3 points for the demand equation. So let's see, they pick P equals 0, 1 and 2. So P equals 0, Q equals 10. P equals 1, Q equals 9. And P equals 2, Q equals 6, right? And let's add 2 points. Let's put that here. Two points is enough for a linear equation. So for the supply, All right, so P equals 0, Q equals 0, P equals 1. Or let's go with P equals 2, Q equals 6. Yeah, so it looks like our solution is right because in both cases we got P equals 2, Q equals 6. Okay, so we should be good to go with this. So there is a likelihood that you're going to have to draw stuff like this in the homework or the exam. So it's always good practice to do it on your own. All right, so what points did we have? We had so that's Q here, and P here. And Q goes up to 10. So let's just say this is 10 is here. Yeah, maybe that's a bit small. But yeah, let's put 10 here. And P goes up to, what was it? Yeah, a bit more. So maybe let's 2. So let's have until 5. Yeah, anyways, let's have this be the same. So it's okay. We don't need all that much. But let's use the grid. Okay, so I always pick blue for the man, but yeah, you don't have to. So 0, 10. Let's just put them there. And then 1, 9. And 2, 6. That's like this. So it should look something like this. Yeah. Actually, I should maybe compute this point there. So if Q equals 0, then P equals square root of 10. Okay, yeah, that's not so good. Square root of 9 would be 3, so square root of 10 would be a bit above. So like here, more or less. It looks, this looks funny a bit. All right, maybe that's right. And then for supply, I have 0, 0, and 2, 6. So 0, 0, and 6 and 2. So that's right. So I can have my nice supply curve. Okay, so well, please, if you draw a graph, say what's on your axes and put some, some additional information on what you have there. Okay, and we're going to say that this is Q. Yeah, it's rather the opposite, right? So you could say it's PD of Q because it's there's really it's like the inverse demand. And here that would be Q PS. Yeah, it would make sense. It's like this is a function of this. It's either is either, so but I would be happy with this. And here we can see this is 6, this is 9, and this is 1, 2. And that one is square root of 10, so I'm not writing it. All right, so that's, yeah, I would say that's good enough. And you can see that this is the solution. So that's Q star, P star. Oh, yeah, all right. Questions about this? So that's the kind of thing that you may have to do. So you indicate what's there, what are the interesting numbers. All right. So going back to our class. Yeah, that was silly. It's not a set, it's a order paired. Sorry about that. All right, something like this. And now the fun begins. Higher order polynomials. Polynomials with rational roots. All right, so if you have a higher order polynomial, but I didn't give you the cubic equation or the quartic equation, or there's no quintic equation anyways, is there a way to solve it? Yes, there is. So it's our friend Gauss, probably the greatest German mathematician of all time, and maybe the greatest mathematician ever, who discovered it. So how would we solve it? So imagine I have of course, if I have my computer, that's easy. So if I have something like 2x minus 3, then x plus 1, and x minus 5, for instance. Now, yeah, that's the result if I multiply everything, so I get this. So I haven't told you that this is the answer, okay? And we have to figure it out. How do we find these roots? Well, what you have to understand is that what is this 2 there? 2x3, it's this term here. 2x times x times x. So that's 2x cubed for you. What is this term here? It's minus 3 times 1 times minus 5. And I don't know exactly how they are distributed, because here what is going to be, oh, so yeah, of course, what I want to find is equals to 0, right? So yeah, what I want to find is this. All right, So what I want is I want to recover this form from this form, because if I have this form, then I know that my three roots are so these roots. So this, what's the solution for this to be 0 is x equals, you know, yes, 3/2. For that one, x equals -1. And for that one, x equals 5. So what I want is to recover these three roots, which are obvious in this case, but not obvious at all in this case. Because I don't know how this 15 was made, or how this 2 was made. Is there a 2 here or a 2 here or whatever? But in some ways, I know that this is a sort of, it's a multiplication of all the factors, sorry, this 2 here, it's a multiplication of all the factors that goes in front of the x's. And this is a multiplication of all the constant terms. So what we are going to know is that the roots, the root, which are 3/2 - 1 and 5, are somehow fractions that come from either the constant term there or the terms in front of the x here. So how are we going to do this? So there is a recipe and we apply it. It's not infallible, but it's quite good. So it works, of course, if the roots are rational, meaning you can express them as ratios. Many things cannot be extracted as ratios. So if you have something like x squared equals 2, so you get that x equals plus or minus √2, and this is not rational. So there's you can prove that this is not rational. So it's not going to work. You don't have it's not going to have have an expression like this. So, but of course, at the exam, I'm going to, if I'm asking you, please find the rational roots, I'm going to give you something that has a rational root, right? Okay, so how do we find it? Well, what we're going to try and find is all the potential candidates for the numerator of these roots and the denominator of these roots, and combine them all together. All right. So, and they can all have negative or positive signs. So I think the best way to go about that is to just find the positive, the potential positive numerators, positive denominators, and then combine them in with the plus or minus sign. So here we go. So let's go step by step. So this is 2, and this is 15, and this is how we're going to yeah. So oh yeah, so first of all, what we can do is just divide by 2. That's, but yeah, we don't have to, but yeah, no, let's just go ahead and do that. So possible. So positive numerators. I have 1, 3, 5, and 15, right? Because this is 15. All the possible denominators. So I have a 2 here, so that's quite easy. I have only 1 and 2. So now all the possible roots, I'm going to combine all these numerators and denominators together. So it's a Cartesian product in a sort, but then I divide them, and then I have to combine them with pluses or minus. So all the possible candidates. So I'm going to have, so let's use all the possible version of the positive values of the numerator and the denominators first. So let's go with 1. So 1, 3, 4. Let's just to not mess with you. It's 1 and 2. So I have a 2 here. So that the two possible dividers of 2 is 1 and 2. That's it. Right. And if I had like 2 over 10, like if I have 0.2 here, so the only thing I would have to do is multiply all my equation by 10. So what I want is a whole number here and yeah, whole number here. Yeah, that's what I want. So I would have this 3 over 1, 5 over 1, and 15 over 1. And then I have the same with using the 2. And then, of course, here I just put the positive potential numbers, but I did that because it's simpler. But now I have to add all the possible numbers with -1s to in front of them. So this. All right. So these are all the candidates. I know that my root is somewhere in there. And yes, I can check. So I have 3 over 2 that's here, -1 that's here, and 5, which is here. So now I'm just, what do I have to do? I have to check. So let's go ahead and do that. So it's tedious. So I'm aware of this, and I'm not giving you two, but because I could give you something crazy with crazy numbers with so many dividers that it would just take forever. So I'm mindful of this. Don't worry. All right. Oh, by the way, how long do we have? We started at 15, so we got until, okay, all right. 2.5. So yeah. So let's start with the first one. So this is, and of course I have a computer, so it's much faster. So let's start with 1. What do I get? 8. So no. Now let's try the second one. 3 over 1. -24. No, that's not it. Oops. 5. Zero. I found one. Yes, that was it. That was here. So now I know I've checked this, and I found one. So then what I can do is, so divide my, I know that I can divide my potential denominator by 5 because the 5 is extracted from there. And I can divide my numerator, sorry, by 5. And I can divide my potential denominator by 1 because I found 5 over 1. So now, so we found 5 over 1. Let's divide by this. So let's divide our. Okay. So yeah, the new constant term we have to work with is 15 divided by 5 equals 3. The new denominator, yeah, I should have said the new numerator, the new denominator is, so here there's no change, it's 2 divided by 1 equals 2. So we do the same thing. So potential, now I have 1, 3, and 5. And then here the potential denominator 1 and 2. Then I go ahead and combine all of them. So I'll just not divide by 1 this time. 1, 3, 5, and then 1 over 2. And 3 over 2. And 5 over 2. And then I can take all the negatives. And then what I can also already remove is 1, since I already tried it. And 3, since I've already tried it. And what did I find? Yeah, 5 I already found it. So 5 is a go. And that's our new choices. All right, so we continue our journey and we try stuff. I'm going to show you later another way you could do it to simplify your life, but it takes a bit of time before. So let's try with 1/2. So no. Let's try 3/2. Zero. So yes. We have the second one, 3/2, and we have one last to find, which is -1. So that's easy in a way, because now we exclude almost everything. So yeah, so now the denominator becomes 15 divided by sorry. So we found 3/2. The new numerator we have to work with is so that was 3, so it's 1. Yeah, 3 divided by 3 is 1. The new denominator is 2 divided by 2 is 1. And we already excluded the 1, so here we can know that. So we use the last root last -1. All right. So that's how you do it. So that's something you have to practice. So I'm going to probably I'm going to post something to solve after the class. I think I didn't make an exercise. Yeah, no, I didn't make an exercise, I think. So I can, oh yeah, one thing we can do now is we can see for ourselves. Oh yeah, so just to conclusion, the three roots are 5. What was the other 3 halves? And -1. So if we order them, that's -1, 3 halves, and 5. And the polynomial is so x plus 1, x minus over 2, and x minus 5. Was it what we had? Yeah. So of course, yes, now what I can do is just multiply by 2. So I can find out what I had at the beginning. So we can see for ourselves. So what I'm going to do is go on Google and just plot this equation, see what we get. Then come back with the result. Okay. Oh yeah. All right. So what do I see? -1. Yes, here -1. 3 halves. Yes, this one, and 5. So we see that we indeed get something that's cubic, and we have our 3 roots here. All right. So I'm going to give you some way to practice it, and you're going to have to do it in your homework. Now I can tell you, yeah, I have to tell you 2 things. So one is something that you may do to simplify your life, and also something that may go wrong. So yeah, some other route you may go to try. So here, when we found our first root, we found 5/1. So what we did is we said, okay, well, let's at least get rid of some. So we know that 15 cannot, we don't have to deal with 15 because 5 is already found. So it was multiplied, something was multiplied by 5. So we got rid of it, and now we only have 3 to deal with. And the denominator, well, we had 1 and we got rid of it, but we still had a bunch of candidates to check. So would there have been another way to get rid of more potential solutions? Yes. So one thing that would have been possible is to divide this by this factor, which we had already found. So we found that 5 was a root, so x minus 5 was a factor. So what we can do is divide this and then get a simpler solution or a simpler problem. Get x minus 5 multiplied by something that is quadratic, and then that's much faster to find. So how do you divide? I may have learned how to do that in high school, but I have totally forgot. So after we found x equals 5 as root, we may want to divide the polynomial by x minus 5. So this is, I guess there are many ways to do it, but here's a way I figured out worked for me. So you may try it yourself. So the thing is, you have to extract x minus 5 from x3, x2, x, and yeah, you have to find how it fits in there. So here's how I see it. So here, rather than having two, yeah, so I'm just going to work with it. So I'm going to say this. So 2x is equal to this, because to itself. But here I'm just going to write this way: x squared times x, okay? And this x here, I'm going to subtract 5 and add 5. Haven't changed anything, so it's still x squared multiplied by x plus 0, so x squared by x, right? And so now what I can do is just take it out. Take the minus plus 5, I don't need it. So plus 5 times 2x squared, so that's 10x squared. 10x squared minus 11, that's minus x squared. And I can do the same. So that's x times x. Here I'm going to say it's minus 5 plus 5. So I don't need that one. So it's minus 5x plus 2x. So that's minus 3x. And here I get, so x minus 5 plus 5. Yeah, maybe that was unnecessary, but yeah. Just to do all the steps. So yeah, minus 15 plus 15, so that's 0. Yeah, I could just have said this is 3 times x minus 5. Minus 3 times x minus 5. So then I get this. X minus 5 times this and this. So this is just, you can solve it easily with quadratics. So I get that x equals so I get, that's 24, 25, so plus or minus 5. Yeah. So I get 2 solutions. So 3 divided by 2. And oh no, 3 divided. Yeah. And minus 1. Yeah. So here you go. Right, so that's another way of doing it. Another way of doing it is approach is just continuing with this thing. It still works. It's still a valid way of doing it. So potential continue with the simplified quadratic polynomial. Potential numerator. So that's 3 and 1. Yeah, positive numerators. It's 3 and 1. Initial positive numerators. So I get, yeah, 2 and 1. 1 and 2. Oh, sorry, 1 and 3. And 1 and 2. So you see that it's a simpler problem, but you have to go over this, this division there. So you see what you want to do, all right? So I've been going quite fast, so maybe it's just if somebody needs to stop me and ask me what I did at some point, go ahead. Which approach is crucial? What I'm going to ask you is please find the rational roots of, so I'm going to say, please find the rational roots of this polynomial, and you do your best. So using a technique that we've learned in class. So if you have a, if you say, oh, my technique is I go on Google, I type the equation and I look at where the zeros are. This is not a technique that we've, well, I've shown you that you can do that in Google and indeed find that the roots are -1, 3/2, and 5. But that's not something that's considered valid knowledge. So you do the best you can. So you don't have to use any technique, but I advise that you learn all of them, that you become familiar with them. Yes, so well, you're free to not learn part of what you don't like about this class and start with maybe 90% instead of 100%. All right, so last thing I want to say is potential problems. So what are the potential problems with this approach? So if we go back here, so what can you observe here? Here we have 15, and here we have 2. And neither 2 nor 15 have common divisors. So that's how we knew that 1, 3, 5, and 15 were interesting numbers to look at for the numerators, and 1 and 2 were interesting numbers to look at for the denominator, all right? But what if you had common factors in there that you could simplify? Then we might possibly be in trouble. So for instance, if there are common factors in the numerator and the denominator. So sort of thing that could happen is if I have like, I don't know. So let's 3x minus 2 times, let's go with 2x plus 3. So you see that I'm using the same kind of stuff for the constant term and the numerator of x. For the second method, anyways, I realized that this method is not like something that you can, that allows you to avoid the first method, because how did I find 5? I went over this, I went over all these candidates. This is still valid. This starts, the second method starts when I find the 5 here. So you still have to try some of them. So you still have to sort of go and look at all the potential candidates. You still have to do that, right? So it's not like you can just, this is when, once you have one root, then it gives you one factor. It gives you as factor x minus 5. So you know that you can divide by x minus 5 and you get a simpler thing. So I'm not sure I understand your question. What do you mean by I only need to find a factor of the constant? Once I did that, then okay, perfect. All right. So let's see if I can put us in danger. So if I have like x minus 1 here, so what am I going to get there? Yeah, so I'm going to get there. Oops. So in this case, I don't know, it looks like you could see that there's something going on. Thing is, I'm not sure, but so if so, yeah, I would get this. So I can pretty much see that I have to use 2 and 3 potentially here and 2 and 3 potentially here, because it's sort of impossible to simplify this, right? But if I don't know, if I did this, for instance, so if I said this is 1 over 6, 11 over 6, and 1, and then I said, oh, well, potential numerator is +1 or -1, or potential denominator is +1 or -1, then it just gives me 2 factors to work with. And I'm kind of, I don't know what to do. So here I sort of have a inkling that something is fishy because I have these fractions there. So maybe it gives me the idea that I have to multiply by 6. But I'm not guaranteeing that it's always going to work. So at least make sure all coefficients of all terms are whole number. Sorry. Yeah. So yeah, this is going to help you, but I'm not guaranteeing. I think you can still have problematic cases in which this won't work. So how would that? How can I do? Let's try with. So if I have, I don't know, maybe I have x minus 2 here. So just to mess around with everything. So what do I get there? Yeah, it still is. I would still have my 6 because I can't divide by. Yeah, okay, it looks like it's working. Anyway, so make sure that you have all numbers there. All right. So what I'm going to do now is close this, then compute something for you to work at home. All right. And we're going to, or do you have extra questions? No, so I'm going to post the exercise for the TA session the Friday. You probably will have stuff like this to work with. And all right, so just wait a second. I don't want you to see what I'm going to use for practice. Okay, so try this, or find the roots of this equals 0. So I'll post that on the website. So please do it if you want to practice. This should occupy you. Okay, so if there are no other questions, then I can say I see you Wednesday.